going to talk global QCD analysis of Pion distribution functions. Please, you can start.
Okay, thank you very much. Thank you again to the organizers for the opportunity to give this talk and for the invitation. Today, I'm going to be talking about the work I've done with Pion phenomenology. And so specifically, I'll talk a little bit more about Pion Parton distribution functions and the global QCD analysis of that, as well as our ongoing effort for Pion transverse momentum dependent PDFs and recent results regarding that. So this is a global QCD analysis. We have a game plan, and we have to, one, define a structure of hadrons in terms of quantum field theories. And yes, those are defined as PDFs are defined, and TMDs are also defined. And then we can identify theoretical observables that factorize into non-perturbative objects and perturbatively calculable physics. The non-perturbative objects are these PDFs, and perturbatively calculable physics we can do. And then we can perform this global QCD analysis. These non-perturbative structures are universal and are the same in all subprocesses, so they appear in the same way. So specifically, my work has been really on the pions, and pions are a very important particle. They're a Goldstone boson associated with spontaneous chiral symmetry breaking, and as well as being the lightest hadron made up of quark and anti-quark constituents. So you see on the right here is a picture of a pion with the core valence structure of a U and D bar quarks connected with a gluon, and then surrounding is the C quarks and gluons that also contribute to the total momentum of the pion. So a little bit of history about Pion PDFs. Generally, there have been fits that have been done to Drillian, prompt photon data, or both. And so on the left, you see here is from the 90s, this GRS, GRV, SMRS analyses, and they did the extractions of valence, gluon, and C quark distributions at next leading order to Drillian and prompt photon data. In the middle, this was more recently, this is about 10 years ago at this point, which is this Acher et al. Analysis. And there they extracted the valence quark PDFs from fits to Drillian data. And the novelty there was that for their perturbatively calculable physics, they included threshold resummation in their calculation. And so when they extracted the PDFs, they found that there was this characteristic softening at large X of the valence distribution, as you see in red, which is in contrast to the harder fall off from the next leading order analyses as in SMRS and GRS. So this middle plot was really one of the major motivations for the work that I'm going to show today, where I also have implemented various threshold resummation methods and extracted PDFs in that way. Additionally, more recently, about a year ago, the Exfritter group also did a next leading order analysis in extracting valence quark, C quark, and gluon distributions to available Drillian and prompt photon data. So in the JAM framework, what we really focus on is the Drillian data, as well as leading neutron. So the majority of my talk today will be focused on Drillian. So I'll only spend a little bit of time talking about the leading neutron. But here in Drillian, what we have is a pion beam incident on a nuclear target. And what I show here is the kind of leading order diagram, in which we have a quark, an anti-quark being donated from each of the hadrons, which annihilate, forming this virtual photon, which then decays into a lepton pair, which is detected. And so this leading order diagram here is the perturbatively calculable physics that is the most important diagram. So I'll talk more about corrections, QCD corrections, namely on this channel. Additionally, in the leading neutron process, we have the electroproduction. This is a tag deep inelastic scattering experiment. So you have an electron beam incident on a proton target, and this proton splits into a pi plus meson and a neutron, where the neutron is detected in the far forward region. And then this split pion is broken up by the virtual photon. And so effectively you have a DIS on a pion. And so we can access the pion structure through the Sullivan process using these available data. So let me just show you what the kinematics are for these data. And so this is Q squared versus X pi, where X pi is approximately a momentum fraction of the partons inside the pion. What we see here in the red circles is the available Drillian data. So we notice that these Drillian data live really at high X. So the Drillian data is good for constraining the valence distribution in the Pion, which is largest at high X, but it does not do a good job of constraining the C-quark and gluon distributions, which really live at low X. Luckily, we do have access to these leading neutron data, which do live at low X. And so we can get a good mapping between the high and low X regions by making use of these two data sets. However, you notice that there is a very little overlap between these two regions. So we look forward to more data and more observables that can kind of fill in this middle region so that we can really test the universality of these PDFs. So we performed this analysis in 2018 at next to leading order. And if we fit only to the Drillian data, then we get the lightly shaded bands. So we can see that at high X, this is well constrained, but at low X, there's really no data there. We find that the C-quark distribution and the gluon distributions have large uncertainties and are not well constrained. However, when we include the leading neutron data, we get the solid bands, and those uncertainties shrink because there's actually constraints on the data and they're more trustworthy in that low X region. So additionally, there's this yellow model dependence, which is model dependence for the proton splitting into the pi plus and the neutron. And we find that in the case of these data from Hera, that model dependence is quite small. So let me discuss a little bit more about the theoretical input, specifically when I'm talking about the Drillian. So this is kind of what I just showed with the Drillian process. So I just wanted to show some formulas here, and really what this means is that this is these are PDFs convoluted with this hard cross section here in green. So PDFs in purple convoluted with the green boxed hard cross sections. And so if we have improvements on the green part, the hard cross sections, to our knowledge from QCD, then we can separate a little bit more from these purple PDFs and can learn a little bit more about the bare internal structure of those PDFs. So really what I want to focus on today in this PDF discussion is with threshold resummation. And so when dealing with the fixed target Drillian data, which is where the Pion data is fixed target, it notoriously has a large XF contamination of higher orders. And these appear as large logarithms in the perturbative calculation. And so these large logarithms could potentially spoil the perturbation. And so threshold resummation is a way to address that. And like I said, these are going to be focusing really on the quark anti-quark channel. That's the most important channel. So the QCD corrections on that will be the most important corrections. So you see here, this is kind of a picture of what is happening. This is a quark line coming in, and then we have some soft radiated gluons. All these Z sub 1s and Z sub 2 and so on, they're all close to 1. So they're the major contribution to the large logarithms are when these Z's are close to 1. And so the aim is to really be able to resum these contributions to all orders of alpha S. So we can see the first kind of issue coming in at next to leading order in alpha S. And the hard cross section has a term that looks like alpha S times log of 1 minus Z with the plus distribution. In terms of hadronic variables, that gets mapped into alpha S times log of 1 minus tau, where tau is Q squared on S, where Q squared is the invariant mass of the virtual photon squared, and S is the incoming center of mass momentum squared of the hadronic system. So if this tau is near 1, then you can imagine that this alpha S times log of 1 minus tau could be large and potentially spoil the perturbation in alpha S. So we can make improvements by resumming these terms that look like this log of 1 minus Z plus. So in practice, these threshold resummation calculations are done in Mellin space. And so those large logs of 1 minus tau get mapped into large logs of n, where n is the Mellin conjugate to tau. And so if we're performing a next to leading order calculation, for instance, then what we do for the perturbatively calculable physics is we sum up all the terms that appear in the rows. And so these are just orders of alpha S to the 0 plus alpha order of alpha S. However, when we include the threshold resummation calculations, we want to sum up all orders of alpha S, and we really focus on the logarithms and the leading logarithms and next to leading logarithms and so on. So for instance, in the leading logarithm tower here, we have terms that are order alpha S to the K times log of N to the 2K. And so these are the most important logarithms. And so these are the leading ones. And then in the calculations that I will show, that we have implemented next to leading order plus next to leading log. So we also include some subleading logarithms. Additionally, these yellow terms you can see appear both in the rows and in the columns. So when you're summing up everything in the rows and summing up everything in the columns, make sure to only count these yellow terms once. So I mentioned that there are some different ways of doing threshold resummation. So I wanted to point out a little bit why that is the case. So when performing the threshold resummation calculation, we do this Mellin transform. And in conjugate space, what we have to do is we have to evaluate some integrations from K perp squared, where alpha S is evaluated at K perp squared. So you can notice that if you look at the upper limits of these integrations, where Z is 1, and then up here, this goes 1 minus Z squared Q squared, this will go to 0. And so that implies that alpha S is evaluated at K perp squared is equal to 0. And that is what's known as the Landau pole, and that is not well defined. So there are some ambiguities on how to deal with this. And so that provides one way to, one need for prescription. So in practice, what we do is to make use of the minimal prescription, which was brought up by Catani et al. In the 90s. And what we do really is to avoid the Landau pole because we know exactly what that looks like in Mellin space. So that's all well and good for the mass distribution, where d sigma dq squared. But when we have the rapidity distribution, so d sigma dq squared dy, where y is the rapidity, this adds a little bit more complications. And the reason we're focusing on this is because that's what the Pion data have. It's doubly differential. And so in doing so, this threshold resummation is done in conjugate space. And so we can perform a Mellin Fourier transform, where the Fourier transform accounts for the rapidity. And so in doing so, there's a cosine that appears in the calculation. And the argument of the cosine is near 0. So you can take the first order expansion, where cosine is approximately equal to 1. And I call that the expansion method. Alternatively, you can take the cosine as just the cosine, keep it intact. And that I will call the cosine method. And then on the other hand, you can, instead of doing the Mellin Fourier transform, you can do a double Mellin transform. So I've highlighted here, there are 3 different ways that you can implement the threshold resummation. So the expansion method, the cosine method, and the double Mellin method. And so what I do in this analysis is to implement these 3 different kinds of methods and perform the Monte Carlo global QCD analysis, explore the different methods, and analyze the effects from each of these methods. So let me just a little bit talk about the methodology in the JAM framework. So we make use of the Bayes statistics. And so this is Bayesian inference. And so to describe the posterior distribution of the parameters given the data, this is proportional to the likelihood of the data given the parameters times the Bayesian priors, which is a function of the parameters. Bayesian priors is kind of what we put in to constrain things, such as like the momentum sum rule. And the likelihood function is Gaussian in the chi-squared. So we have to maximize the likelihood of the data given the parameters, and so that effectively goes into minimizing the chi-squared. So what I show here is what we use for the chi-squared, and let me just walk through a little bit these terms. So we first sum over all the experiments. And then inside of that sum, we sum up over all the data points. So we have here this data, d sub I, and then we subtract off the theory here. T sub I is a function of the parameters. So this is how we would calculate the cross-section in our codes, given the parameters where you parameterize your PDFs. And so that has some multiplicative factor that's shifting it, and that's this n sub e. This is a normalization parameter that is a fit parameter that is determined. It's influenced by the normalization parameter the normalization uncertainty associated with the experiments. And so we're multiplying that by this, so the theory by that. And then this middle term here is this shift term, where the betas here are represented by the correlated uncertainties. So in essence, what we have is this theory that we're calculating. We have this multiplicative factor of the normalization, and we also have an additive shift here. This is dealing with the correlated uncertainties. So what we're comparing with the data is really this t divided by n plus this shift. So that's data minus this theory all over the uncertainties alpha, where alpha is the uncorrelated uncertainties added in quadrature. And then what we have is some penalty terms for the normalization. If the normalization is too far away from the reported uncertainties from the experiments, then there's chi-squared penalties here. And also if these shifts need to be too large, then there's some penalty from these nuisance parameters R. And so this is a Monte Carlo framework. So what we do is we implement this chi-squared many times. So we perform it a total of n times, and then we can compute statistics in the Monte Carlo framework. So such as the expectation value, which is really the expectation value of some observable is really the average of those observables. And then the variance is calculated in a similar manner. So let me discuss the results that we have for the threshold resummation analysis. And so let me show here what the data and theory comparison is. So what I show is the data divided by theory. And in red are the next to leading order points that we got from the next to leading order analysis. And then in green, blue, and yellow are the cosine, expansion, and double melon methods. So immediately, one thing that we notice is that at low xf, that all of these methods tend to give similar descriptions of the data. Nothing is too much different. But when you look at really high xf, namely even higher than xf at 0.8, you start to see that there's major deviations from these threshold resummation methods. So for instance, here at high xf, you can see that the red and the yellow tend to give similar agreement to the data. So the next leading order and the double melon methods, whereas the expansion and the cosine methods tend to overpredict the data at large xf. So we can tell that this is clearly a large XF effect. And so this large XF effect really gets mapped into the valence quark PDF at large X. So what I show here in this top left panel is the valence quark PDF through all these different resummation methods. And so what we show for comparison is the next leading order, which is very hard at high X and linear fall off. But if we include the threshold resummation, then we have some softer fall off, but the degree of softness varies depending on the implementation. And so in the bottom row, also what I show is the truncated moments. So what this means is where in X do these flavors gather their momentum fraction? And so you can see at large X, when we had the next leading order analysis compared with the threshold analyses, threshold resummation analyses, there's a drop off in the momentum fraction in large X for the valence PDF. So where does that go? Well, it turns out this large X momentum fraction actually gets spread into the gluon at smaller X. So where the deviations from the next leading order are more apparent starting at smaller X in the gluon PDF. Additionally, we can describe the large X behavior of the valence quark distribution as this 1 minus X to the beta. And so what I show here is the effective beta parameter as a function of X at large X. So in the red, as was expected before, we had the next leading order analysis. This was had a behavior as 1 minus X to the 1 power. But when we use threshold resummation, there is not a universal behavior of this beta parameter. So this actually varies. When you use this double melon method, you have something that's a little bit closer to the next leading order, more consistent with a linear fall off. However, when you use the cosine and expansion methods, what you find are their beta parameters are larger than 2. So there's quite a difference. There's a variance in all these threshold resummation calculations.
5 minutes.
Okay, thank you. I will focus, I'll just spend the last 5 minutes here talking about the transverse momentum dependent Drillian. I'll try to go a little bit more quickly through here. Traditionally, this has all been done with PT integrated Drillian, but we also included for the first time PT dependent Drillian data in a global QCD analysis. So the spectrum for the PT dependence is unique in that at small PT that you follow some TMD factorization, where the PT here is coming from this partonic transverse momentum inside of the hadron. But at large PT, you can't really describe the large PT of the virtual photon coming from those intrinsic partons. So it's actually coming from a recoil and of a recoiled parton coming off of a parton line in the hard part. So this follows collinear factorization, and there are different varying regions in the PT spectrum where these hold. So this is, for instance, the fixed order analysis that we performed with including the large PT dependent Drillian data. So you can see in this diagram A, this is still quark anti-quark annihilation, as was in the PT integrated case, but we have some recoil gluon here that has some PT kick, which gets transferred into the virtual photon. So we found that this was largely the same as just doing an analysis with PT integrated Drillian and leading neutron. The uncertainties of those large PT points in Drillian are quite large, so those do not dramatically affect the PDFs. What we found was that there was a successful description of the data with a scale mu is equal to PT on 2. Additionally, we can look into the small PT region, and we use CSS formalism for the TMD evolution. So effectively for this triply differential cross-section, this is effectively 2 TMD PDFs multiplied together. So there's a few non-perturbative TMDs that we can extract by looking at the small PT data. And so these are this G sub J, which is associated with this hadron A, and G sub J with associated with some hadron B, and those contain some non-perturbative physics. Additionally, there's this G sub K. This is a universal quantity and is hadron independent, flavor independent. It appears in the same way in each TMD PDF, no matter what. So what we do here first is to approach with a leading order analysis for all these hard coefficients and diagnose what the current situation is. So in looking at the Pion data, this is Pion on a nuclear target. So we have to have some notion about what the nuclear TMD is. So we also look at the E288 proton platinum data, and we simultaneously fit the small PT TMDs to the E288 and the E615 data, where the E615 is the Pion data. And so this is what I'm showing here is the proton data. And so you can see here at low PT, we have these fitted points in red, and this blue curve is the W term. That describes well the data at low PT. So the W term is really this TMD factorization. And then in the green is this fixed order, which is the collinear factorization. And what I show here is actually a pretty good agreement with the data, even though this wasn't a fit. But I used the scale mu's PT on 2 as what we found with the Pion case. So additionally, this is the results for the Pion data. These large PT points are what was fitted with I just showed from the collinear analysis, but we also fit these low PT data at the same time. We get some good description. So there's some region in here in the middle that is that there's some similar description with the W and the fixed order term. So we'd like to look a little bit more in this matching region, so to speak, which is more of a theoretical open question. So let me just quickly go into some applications and summarize my work here. So we're really looking forward to the new future experiments, such as the TDIS experiment at JLab, which is complementary to the Hera leading neutron experiment, which will give some leading proton observable, as well as we're looking forward to the COMPASS ++ AMBER results, which will have some Pion-induced Drillian data. Additionally, we can look forward to the EIC. And so there was this ongoing effort for the yellow report. And one of the things that we looked at was the impact on the Pion PDFs. Since the integrated luminosity of the EIC is so large, what we find is that the statistical uncertainties are dominated by the systematics. So you can see here what I show is the statistical uncertainties in the circles and the systematic uncertainties of 1.2% in the magenta boxes. And so for most of the region in X, you find that these are dominated by the systematics. So if you can really get the systematics down in the experiment, then there's really some hope for some high impact on the PDFs. So let me just show what the PDFs would look like if we included these EIC data. And you can see on the left, these are major reductions in the uncertainties of the PDFs. And so I show a similar kind of thing a little bit differently. And this is the uncertainty of the PDFs with the EIC over the uncertainties of the PDFs without the EIC. You can see, for instance, the valence distribution uncertainty reduces by about 80%. And depending on where you are in X, the gluon and C-quark distributions reduced by 70 or 90% even. And the uncertainties on the momentum fractions for the EIC over the uncertainties, momentum fractions without, you see that the total quark and total gluon momentum fraction uncertainties will reduce by about 90%. Okay, so I'll just leave this slide up. We have some other prospects that we'd like to, and I'll take some questions at this point.
Okay, thank you very much. Are there questions?
Paul Hoyer here, hi. As I recall, at large XF in the E615 data, the angular distribution of the virtual photon changes to be sine squared theta, so there's like higher twist effects. Can you say anything about how you handled those?
We have not handled higher twist effects. This is all just a leading twist.
But if you have a sine squared theta in the polarization of the virtual photon, then it's not leading twist.
I see. Well, we will have to consider that. This has not been considered.
There's an old paper by Berger and Brodsky where they discuss this.
Thank you.
Chao Ji.
Hi. Hi, Patrick.
Hi.
Yeah, could you turn to page 30?
Yep.
Yeah. I was wondering, the transverse momentum dependence, I think it's one slide before this. How do you determine those non-portability of transverse momentum dependence in all these three elements? I mean.
Yeah, so we have some parameterization for these, and we have some functional form that we use, and we calculate the cross section, and we perform a least squares fitting on that. Minimize the
I see.
Yeah.
I see. Okay. Thank you.
Yep.
Yeah, Craig. Craig. Unmute your microphone, Craig.
Thank you, Gaston. Sorry, Patrick, I was talking to myself for a while. I liked the presentation. Thank you very much. The discussion of the Landau pole and the role it plays in your next leading logarithm resummation. Have you tried using the fact that QCD doesn't have a Landau pole, that the running coupling actually saturates in the infrared? And how would that affect your results?
That's an interesting point. So let me go back to here. That's an interesting point, and no, we have not really considered that. What we really do is we actually approximate the Mellon transform, where this does not go all the way up from 0 to 1. This goes from 1 minus some smaller factor. And in that case, we can actually perform this analytically using some analytic form for like 2 loop for alpha S, and then go in and calculate the resummation terms. So no, we have not considered that. That is something that is kind of intrinsic, I think, to many of these threshold resummation calculations, is this kind of Landau pole problem. And as far as I know, not much in the literature has been said about doing a threshold resummation with this saturation, as you put it. But that's an interesting point.
Is it something you could explore? Is it within your capabilities?
In principle, if we have something for the alpha S, but what we use for our alpha S is something that does follow something that would have a Landau pole. So we do not have, in our calculations, our alpha S is not saturated at at low scale. In principle, this could be done, but I don't know really the amount of effort that would be put into actually do that.
Just to ask it a different way, if you had an alpha S that's saturated, there's no reason in principle why you couldn't use it, or there's something in the framework that you're employing that prevents you from using a saturating alpha S?
Just in our codes that we have, this alpha S appears in many places, and so we have something. But we would have to change that alpha S, and in principle, I think it could be done. And in practice, we could recalculate the threshold resummation coefficients that actually are following based on this. And that way, you don't have to have this kind of approximation of the Mellon moments. That could be done in principle. I don't see a reason that it cannot be done. But as far as I know, this thing has not been done.
Okay, thank you. I'll send you a link to an alpha S that saturates.
Okay, thank you.
Yeah, Victor?
Thank you very much for your talk. My question is, you mentioned that all your insight into PDF is in leading twist.
Yes.
So it is well known that at least for nucleon, at high X and low Q square, power correction are important. What is specific for a meson structure? Why you neglect by power corrections?
Well, looking at the kinematics, we really don't have Q squares that go down to small enough Q squares that may be important for a nucleon, because there is nucleon data at very small Q squared. But here you see in the Pion data, the smallest Q squared for the Drillian, for instance, is about 15 GV squared. So I think that is enough to where we can ignore those higher effects.
I agree that at 10 GV square, you can easily forget about this.
Mm-hmm.
Okay, we have 2 more questions. Can we leave them for the discussion session in 30 minutes? Is that okay, or is something really urgent? Okay, we leave it for the discussion session. Thank you, Patrick.